paved surfaces like road surfaces, and to crops and to forests. And it also measures things related to weather satellites, that weather satellite people that want to know about what use. So it measures many different parts of the spectrum. Then you get to Landsat in the third row. In Landsat 7, that's called L7, and it's got an acronym for the instrument called ETM, Enhanced Thematic Mapper. So it's ETM Plus. And it has 4 bands in the visible and the infrared. It has 1 panchromatic band. That's the narrow, small, wide line that crosses from about 500 nanometers to 900 nanometers. So it's both in the visible and the near infrared. And that's the panchromatic band for Landsat 7. And it has blue, green, red, and near infrared bands. And then it has 2 bands in the 2 shortwave regions. And it has 1 large band, covers a lot of wavelengths in the thermal part for a single thermal band. Then you have Landsat 8 and 9, which is the next higher row. It has a lot of the same. It has its panchromatic band. Band 8 is a lot narrower than the one that was used in the Landsat 7. You can see it's about half the length, meaning half the wavelengths. But it has an extra blue band. You see it's a little bit higher. It's a lighter color blue than the dark blue. So the blue, green, and red, the standard blue, green, and red are bands 2, 3, and 4. But band 1 is that extra blue band. That's for people that do oceanography are interested in that because it's important for observing in the ocean. And then it has a band at both band 6 and 7 are in the same positions more or less as the 2 bands that were in Landsat 7, but it has 2 thermal bands, 10 and 11, and they're much narrower wavelengths than the old one. And part of that is because as the technology has progressed, it's easier to have instruments that measure smaller segments of the thermal infrared and get good data, and they're more stable and they are not as heavy as they used to be. So anyway, they decided to get 2 bands in the thermal region. If you notice, there was this extra band 9 in around 1400 nanometers for Landsat 8 and 9 have this extra band in addition to the band 1. And that's in an area where we don't get any reflectance much from the surface because almost all of the energy is being absorbed by the water in the atmosphere, water vapor. And so why would you put a band there? The gray areas are where we get light gets all the way to the surface. And so those are bands that we can measure surface properties in, are the areas in the gray bands. But for some reason they did that for Landsat 8, and the reason is because they want to measure high cirrus clouds, these ice clouds that are in the high atmosphere, and they're usually very thin, and they obstruct a lot of the light is reflected back from it, and it never gets to the surface, and it contributes to a lot of misidentification in Landsat data, in the older Landsat data. About half the images are contaminated with cirrus cloud contamination that you can't see in the imagery. It looks like you see the surface, but the dynamic range, the range of the values is about half of what it normally would be. So by having this new band in that part of the spectrum, it lets the investigator say, oh, there's a whole lot of cirrus in this image, I don't want to use it, because now you have a way to measure the cirrus clouds and know if it's there or not there. Whereas before you had to kind of guess by how much the dynamic range was. So that's the reason for that band. Anyway, then we go to Sentinel-2, and it has bands that are pretty similar to Landsat bands, if you notice. It has a blue, green, and a red band, more or less a little bit difference in how wide those bands are, the spectral width of them, but they're in the same parts of the spectrum. And then the same with their band 11 and 12, and the Sentinels are in more or less the same position as the 2 shortwave bands in the Landsat 7 and 8 and 9 satellites. You notice there's no thermal band in Sentinel-2, so that's something different between the Sentinel-2 satellite and the Landsat satellite. And but you do have right above the near-infrared in that kind of purple color, you see you have 4 narrow bands that are between the red and the near-infrared. And that covers this region called the red edge, and it's very sensitive for changes in vegetation in terms of its potential for photosynthesis. And so people were really interested in measuring that. And now that the detectors are so much better and the ability to measure photons at very fine scale has improved, you can use these super narrow bands to measure that part of the spectrum. So it added those 4 bands. And then above that, you see 3 bands that are for calibration. And you see it has the same, basically the same band as for the guys want for band 1 for the calibrating for the ocean. It has the same as band 10 as band 9 in the Landsat band. So you have a cirrus band and you have a ocean color band in the blue, and then you have this extra purple band. And those 3 bands are used for helping to better calibrate the Sentinel-2 data. Sentinel-2 is in the same orbit as Landsat. It goes, so Landsat and Sentinel can be used together because they both are covering, they're just offset from each other. And so they, the Sentinels they're a pair of satellites, so they're 180 degrees apart. So you get, each one takes 10 days to cover the whole Earth, but by having 2 of them, you cover the whole Earth every 5 days in repetition. And then the sats cover every 16 days. And if you have 8 and 9 operating together, we'll have every 8 days for that and every 5 days for the Sentinel-2. So if you put those 2 satellites together, the European satellite and the NASA satellite, the US one, you could have coverage of the land surface every 2 to 3 days at the 20 meters of the Sentinel-2 data or the 30 meters of the Landsat data. So it's a huge potential for increasing the frequency of the data. And I didn't say, but all of the satellites I identified are all free, meaning the data is free. It's a free and open data access policy, so they aren't restricting access and you don't have to pay for it. So it makes this data available to U.S. investigators, as the NASA data used to be available to European investigators, but we had to pay a lot of money to get access to their data. So now they're following the same pattern. And that's also pushing, the Japanese are going to make some data free and open access, and other countries are following suit. So it's been that change in policy from having a restricted access and charging a lot of money, which has not been a very successful policy. That's why they're dropping it. It turns out that you can have thousands and thousands of users instead of a few users by just making it freely available. And it really justifies the cost of launching these expensive satellites. So with that, I would go on to my next example. So here's an example of Landsat data. Any of the Landsats from Landsat 4 to Landsat 9 you could use, do the same kind of mapping with. You're basically using a statistical program to identify different patterns of reflectance in your Landsat bands. And if you know something about the site, you can identify what they are. So the colors to the left of the figure show what kind of land cover these different colors are supposed to represent. And you see most of it in this image are some kind of mixed hardwoods, are kind of the bright green seems to be the most common color. And then of the blues, the light blue, like northern hardwoods or red maple, comprise most of them. And then you've got some spruce or some balsam fir, some conifers where it's red. And then the white area is something that was not mapped. So you have an area that probably wetlands that were not mapped in this forest map. But you can see you could use, and that's how much of Landsat has been used, and much of these optical sensors have been used over the years, is to make maps of land cover. and changes in land cover over time.